So, in this video, we'll be talking about the round robin arbitration in interconnects. Please implement the Verilog coding for the round robin arbitration line by line with proper explanation for each of the line in the Verilog code.
All right, let's dive into it. A round robin arbitration in Verilog typically involves keeping track of which requester gets the grant next in a cyclic manner. We can break it down step by step. One, declare inputs and outputs. We'll have request lines from multiple masters and a grant line for each. Two, state variables. We usually need a pointer or a register to keep track of the last granted requester. Three, arbitration logic. On each clock cycle, the grant is given to the next requester in line, ensuring fairness. Four, reset and update. We'll have logic to reset the pointer and update it after each grant. If you want, I can walk you through the actual Verilog code line by line. Let me know if you have any specific number of requesters in mind or any details.
Yeah, maybe we can take 4 requesters. Let us see the line by line Verilog coding. Before that, if you can provide the initial kind of pseudocode or the and the FSM, please go through that flow and then go to the Verilog coding and explain each and every line of the Verilog code and also different parts of the Verilog code and what they actually function while you're explaining the Verilog code.
Perfect. Let's start with the pseudocode and the FSM design. Pseudocode and FSM, 1, inputs and outputs. Inputs RIC 3 by 3 for request lines and clack and reset, asynchronous reset. Outputs 4 grant lines, 1 for each requester. FSM states we essentially have a single state where we check each request line in a fixed order. After granting one, we move the pointer to the next requester for the next cycle. On each clock cycle, if the reset is not active, we check each request line starting from the pointer. The first request line that's high gets the grant, and we update the pointer to the next requester. If no requests are active, no grant is given, the pointer recs around after the last requester. Reset logic. On reset, we initialize the pointer to 0. Next steps, now that we have a high-level understanding, we'll move on to the Verilog implementation. I'll guide you through each line of code and explain what it does. Let's get started.
Yeah, please go ahead.
Great. Let's jump into the Verilog code step by step. Verilog code for round robin arbitration for requesters. 1, module definition and ports. EVlog round robin arbiter. Input wire SCLAC. Input wire said Reki's request lines from 4 masters. Output Reki's grant lines to each master. Explanation, we define a module named round robin arbitrator. It has a clock, clack, a reset, 4 request inputs, Reki's 3, and 4 grant outputs. Internal registers, reg 2 pointer points to the last granted requester. Explanation, we use a 2-bit register called pointer to keep track of the last granted requester. Since we have 4 requesters, 2 bits are enough. 3, grant logic always on positive clack or positive reset. If reset B, reset pointer, reset the pointer to 0. Grant is 4B000, no grants on reset. And else B, a grant Lesky 000, clear grants before assigning new one. Check requests in round robin order starting from the next pointer. If Reki spawn a B1, grant the request at the pointer. And else if recs at point the 1% for is grant the point AB4, grant the next requester, abbing her 1 with second A3, bang 1 pointer, move pointer to next requester, and else if rec 2B4 is grant the A6, so 0 is grant the next requester, pointer A64 is grant, else if rec E4 is grant the next requester, 1.3 is grant the next requester in a turn see a grant and individual explanation in the always blocked. We first check if reset is active. If it is, we reset the pointer and clear all grants. If reset is not active, we start by clearing all grants to ensure only 1 grant is active at a time. We then check each request line in a round robin manner, starting from the current pointer. We use modulo 4 to wrap around the pointer. The first active request line we find gets the grant, and we update the pointer to that requester's index plus 1 modulo 4 for the next cycle. This way we ensure fairness in round robin behavior, and that covers the core logic. If you have any questions about specific parts or want more detail in any section, just let me know.
Yeah, sure. I'll just try to walk through the code again. So initially, during the reset state, we initialize both the pointer and the grant to zeros, and then we are just checking in an if-else condition. Right, rec of pointer is so in case the pointer is at 0, so grant of 0 is 1. If the pointer is let's say, so in case the pointer is the request of 0 is not 1, then it moves to this one. So in this case, request of 0 plus 1 modulo 4, in that case the grant of 0 plus 1 modulo 4. So in case the pointer is still, if the
Exactly. You've got the idea. The process is all about checking each request line in the order determined by the pointer and then moving that pointer forward for the next cycle. If the request at the current pointer is not active, we check the next one and so on until we find an active request. Once we find it, we grant it and then update the pointer to the next requester, ensuring that the next cycle will start from there. This logic ensures that every requester gets a fair turn over time and the pointer wraps around seamlessly after reaching the last requester. If at any point none of the request lines are active, then no grants are issued for that cycle, and we just wait until the next clock cycle. Let me know if you want to dive into any other part of the code, or if you have more questions.
can you explain how this Verilog code behaves in a round robin fashion and gives fairness to each master? Okay, and give let us take an example where the master 1 as a request, and then master 2 as a request, and then the master 1 as a request at the same clock cycle. So how does it behave in that particular scenario?
Absolutely. Let's walk through that scenario. Scenario master 1 and master 2 both request one initial state. Let's assume the pointer starts at 0. Initially, grant is all zeros. Clock cycle 1, master 1 recce is 1, master 2 recce 1, master 3 is 1, master 4 recce 0, currently at 0. We start by checking recce's because the pointer is at 0. Result, since recce 0 is 1, we grant. Grant is 1, update pointer. After granting recce's 1, we move the pointer to 1 for 0 per set of 4, which is 1. Result after cycle 1, grant is 0, 0, 0, 1. Only master 1 is granted. Pointer is 1. Block cycle 2, same as before, master 1, recce 0, 1, master 2, recce 0, 0, 1, others are 0. Now at 1, we check recce's 1 since the pointer is at 1. Result, recce's 1 is 1, so we grant, move the pointer to 1 plus 1%, 4, which is 2. Result after cycle 2, grant is 0, 0, 1, 0. Only master 2 is granted. Pointer is 2 for clock cycle 3. Recce's is same as before. Now it's 2. We check recce's 3. Since recce's 3 is 0, we move to the next one. Recce's 3 is 0, still no grant. Check recce 0. Recce 0, so now we grant 0. Update pointer, move the pointer to is 0, 0, 1, which is 3. So grant is 1, 0. Only master 1 is granted again. Pointers is 3. So same as before. Now at is 3, we check recce's 3. Since recce 0 is 0, we move to recce 0. Is recce 0 is 1, so we grant recce 0. Recce 0, move the pointer to 3, is 1 is 0, which is after cycle 4. Grant is 0, 0, 1. Rest the master 1 is granted again. Key takeaways, fairness over multiple cycles. Each master gets a turn. Even if master 1 requests again, the pointer ensures that master 2 gets its turn next, and then master 3, and so forth. Round robin behavior. The pointer moves to the next requester each time a grant is given, making sure that no master is starved and that each one gets a fair share of the grants over time. Hopefully that example clarifies how the round robin arbitration ensures fairness and how it cycles
Sure, thanks for that. Please provide a conclusion and end the video.
Of course, in conclusion, the round robin arbitration ensures fairness by systematically cycling through each requester and granting access in a fair and predictable manner. By using the pointer and checking requests in sequence, we prevent any master from being starved and ensure that each gets its fair share of access over time. This approach is widely used in interconnects and systems where multiple masters need equal opportunity. Hopefully, this gives you a solid understanding of how the code works and how it provides fairness. If you have any more questions or need further clarification, feel free to ask.
Thank you.
You're welcome.